Hi everybody. In yesterday's video we derived the mathematical expression for output of an ideal sampler. So we derived this expression, which is x delta of t, which is the output of an ideal sampler, is x of t multiplied by a impulse stream, which is summation n equal to minus infinity to infinity del of t minus nts. Today we will derive what we call as Nyquist theorem. And what is Nyquist theorem? We'll talk about it. So in our example, we took x of t, we assume this is x of t, and this is the frequency domain representation of x of t. So x of f has frequency component from minus fx to plus fx. So for our analysis, it's always easier to do analysis in frequency domain. So we'll take this x delta of t, which is the output of ideal sampler. We derived this yesterday, and we'll take Fourier transform on both sides. So x delta of f is equal to, now on the right hand side I have a multiplication of two functions. So we all know the convolution property of Fourier transform, where multiplication in time domain maps to convolution in frequency domain and vice versa. So since I have multiplication in time domain here, it would be convolution in frequency domain. So in frequency domain, x delta of f would be equal to x of f convolution Fourier transform of impulse stream, which is x of f convolution Fourier transform of n equal to minus infinity to infinity del of t minus nts. Now this part x of f, we already know the plot. So now the right side of this part, which is the impulse stream, this is a well-known Fourier transform. So Fourier transform of an impulse stream in time domain is f with periodicity ts, which is a sampling period in our case, is equal to fs, where fs is 1 by ts, into impulse stream in frequency domain. So this is a well-known Fourier transform. So mathematically, Fourier transform of summation n equal to minus infinity to infinity del of t minus nts is equal to fs into summation m equal to minus infinity to infinity del of f minus mfs. So here this n and m are just variables used for summation. I'm using different n and m because these are two different summations. So to clarify, these are not the same variables. I'm using two different variables here. But essentially, impulse stream in time domain, if I take a Fourier transform, it's fs into impulse stream in frequency domain. So now I'll just substitute 2 into 1, and then I get the next one. So x delta of f is equal to x of f convolution. So I'm just substituting equation 2 here, fs into summation of m equal to infinity to minus infinity del of f minus mfs. Now we all know convolution satisfies distributive property. So x of f, fs is a constant, so I can just take this fs out here. Now x of f convolution or summation is equal to summation of x of f convolution with that function. So I can bring this convolution inside the summation, so it would be x of f convolution del of f minus mfs. Now we all know convolution with the del is the function itself. So the final, I just skipped a step here, but finally if you see, you will get x delta of is equal to fs into this convolution will come inside, so I will get, and convolution with the impulse is the function itself, so I get fs into summation m equal to minus infinity to infinity x of f minus mfs. So this is my final expression for the output of the ideal sampler. So this expression in frequency domain, this shows the output of an ideal sampler. So let me just try to plot the frequency domain plot in frequency domain the output of an ideal sampler. So of course fs here is my sampling frequency. So I will take different assumptions of sampling frequency here. We will take first sampling frequency fs is equal to 2fx, which is 2 times the highest. So if you see the original frequency domain representation of x of t, x of f has frequency component up to fx, to minus fx to plus fx, or in other words, fx is the highest frequency component of x of f. So let me just, in this our example, let me just take fs is equal to 2fx and try to plot x delta f. So if you see here, fs is a constant, so when my m equal to 0, this would become fs into x of f. So for m equal to 0, this will simplify to fs into x of f. I know this part of the chart represents my x of f, so it will be just linearly multiplied by x of f. So it's like a triangle, same plot as x of f with a linear multiplication of f of s. So this part of the chart shows my plot when m equal to 0. Now when m equal to 1, this if you see this expression, this would become fs into x of f minus fs. So we all know, again, as we saw yesterday, when the independent variable of a function is subtracted by a constant, the function shifts by that constant. So in this case, since it's f minus fs, this plot will shift to the right by fs, and since fs is 2fx, the plot will shift to the by 2fx. So from 0, this will be centered on 2fx, and we know this was from minus fx to fx. So when it is centered on 2fx, the next plot is from minus fx to 3fx. So this initial one is when m equal to 0, this one is when m equal to 1. Same way, when m equal to minus 1, this would be x of f plus fs. So this will be left shifted by 2fx. So this is when m equal to minus 1, and so on. So when I plot the entire summation, basically I get a continuous plot from minus infinity to plus infinity. So this is how my plot looks like here when fs is equal to 2fx. So basically I see a continuous plot from minus infinity to infinity, and as you can see, this is x of f plot, and then I have other additional frequency components. These do not overlap with each other. They kind of touch each other, but they do not overlap with each other. So on the receiver side, if I use a filter, a low pass filter with a cutoff frequency from minus fx to plus fx, if I use a low pass filter, I can recover back my original signal x of t. So all I need in the receiver side, my reconstruction filter, would be a low pass filter, an ideal low pass filter with cutoff f of x, and I can get back my original signal x of t. Since in frequency domain it is same as x of f, so in time domain it will be same as x of t, as we studied in the previous videos. So this is the condition when fs is equal to 2fx. So now let's take the condition when fs is less than 2fx. So my sampling frequency is less than 2 times the highest frequency component of my input signal. So basically the plot is very similar, just that since fs is less than 2fx, when this plot right shift by fs, this here right shift is fs is less than 2fx. So the center is less than 2fx. So there's an overlap between these two. So as you can see here, so this plot is same as my original x of f plot, but then the right shifted plot does overlap with the original plot. And same way, when it left shift, when m equal to minus 1, there is again an overlap here. So again, similar to fs is equal to 2fx, I see a continuous graph on both sides, but these graphs overlap with each other. So if I want to recover the original signal, if I use a low pass signal, so let me just clean it for a minute. So let's say I want to use a low pass signal to recover my original signal. If I use a low pass signal like this, you can see there's a distortion or corruption in my higher frequency components, because I cannot distinguish my original signal from the additional frequency components that I am getting because of sampling. This corruption, or this is called aliasing. This impact is called aliasing. So another way to say is, when my sampling frequency is less than 2 times the highest frequency component of the input signal, I cannot recover the original signal without any error. There would be some error introduced due to aliasing. Now let's take the third condition, when fs is greater than 2fx. So when fs is greater than 2fx, obviously the original, this is x of f, this is x of f minus fs. Since fs is greater than 2fx, it right shifts by greater than 2fx. So there is a gap between the two. Same way on the left side, fs plus fx, there is f minus plus fs, there is a gap between the two. So because of this, again, there is no overlap, so I can use a low pass filter and recover the original signal. So I think we all can see that when my sampling frequency is greater than or equal to 2 times fx, which is 2 times the highest frequency component of the input signal, I can recover the original signal on the receiver side using a low pass filter. But when sampling frequency is less than 2 times the highest frequency component of the input signal, I cannot recover without any error. So this property is called Nyquist theorem. So just to phrase the Nyquist theorem says a low pass signal must be sampled at more than twice the highest frequency component of the signal. So Nyquist theorem is for a low pass signal, and I think it just describes what we discussed mathematically above. Now before I end this video, just a quick comment. So you might want to ask, why would I ever use a sampling frequency greater than 2fx? Obviously, when I use a higher sampling frequency, I have more samples, which means I need higher bandwidth. So why would I use this condition when fs is equal to 2fx is enough? Well, the reason is that in real world, a filter is never ideal. So if you want a filter with transfer function 1 from minus fx to plus fx, there will always be fall off. It will never go down instantaneously to 0. So there will be a fall off of filter. So you will get all this unnecessarily frequency component from the next graph. So you will still see some distortion because your filter is never ideal. So there will be a fall off which will allow these additional frequency components to get in here. But if you use this case where fs is greater than 2fx, so there is a gap between this additional frequency components. So if I use a transfer function which is 1 from minus fx to plus fx, and there will be a fall off of the transfer function, but because of this gap allows me for this fall off to occur without any additional frequency components getting into the output signal. So in other words, I can recover the output signal without any distortion. So obviously, so because of this reason, so in just to summarize, for an ideal filter, fs is equal to 2fx is enough, but for a practical filter in real world, you would want fs to be greater than 2fx, and typically we use fs is equal to 2.2 fx is generally used in industry. So that's all for today. I think we used yesterday's video and we derived Nyquist theorem and how much in a real world the sampling rate should be. Thank you, everybody.